you see the title is very long. There are some number of undefined words. So probably the most of it will be on this subject, which are generalizations of lines. This I will probably hide until the very end of the talk, because it's a more specialized topic. So it will be a little bit like talked by Martina Remini from yesterday, when she introduced nice objects. So anyway, I'll start with lines. So everything below 3 is vector. And this will be really element space. So let me denote by LE instead of lines. Yes. Okay. This object is a line for a given point. So this set has a sort of scheme, follow scheme of lines. Well, I will just look at it as a set. And I will see these lines through X as embedded in the projectivization of the Zariski tangent space. So this is, as we guess, the Zariski tangent space is the projective space of directions. And the map is quite just this. Send the line to its tangent direction. I'll be interested in the image of this. So the first examples, you see it immediately. Maybe I should use the opposite. So let's start with the most basic example of the thing. Projective space. And therefore, we get all the projective tangent directions. For all points. So the next example is quadratic. And then it's easy to see that you get another quadratic of dimension n-2 in the projective space of tangent direction is now n-1 again. Well, the picture is very easy. Either you write equations, immediate, or you think of it this way. You look at the Zariski tangent space to this quadratic at some point x, and you look at lines in x. They must be contained in this embedded Zariski tangent space, and there are lines in quadratic cone, which is the intersection of the quadratic with x, and the direction of this cone is this 2n minus 2. So that's kind of easy example. Another one, which is more elaborate, is the class finding. So we try to use some consistent notation with other talks. So let me try this one. This one, everyone has its own notation for class lines. This one is, I guess, self-contained. This is the d-dimensional. So this is of its length. So let me describe lines there. Actually, you saw some lines in the talk by Martina yesterday. These were exactly these t-stable curves. And if you think of them, they are actually in line. So let me produce one of them, which is called Schubert line. So what you do is you fix a standard flag. Which is generated by coordinate vectors. Okay. Like in Martina's talk. And you look at the spaces which are contained in the -1 element of this flag, and well, switch between these two subspaces. So these are the V's in this class one, which are somewhere between these V's. And if you think about this is a projective space of E plus 1 of E minus 1. This space is half-dimensional B. And so you get P1. If you write this in coordinates, you find back one of these curves that Martina was constructing yesterday. And the point is to get all the lines in this way. So let me state this. If we take for X leaf spanner space, which is BD. So to get them, I fix two subspaces of dimension D minus 1 and larger one of dimension D plus 1. And I look at all intermediate subspaces. Well, the condition is that we have this, so that they are actually true X. And this is again projective space. And you can check easily that it's linearly embedded in the quicker embedding. So that's a set theoretical description of lines. If you want to understand the space of lines for X, so what you have to get is some D minus 1 subspace of GG. So this is a hyperplane on the projective space of dimension D minus 1. So we write it this. This is for this F, this E, sorry. And then what you also need is a subspace which contains VD in codimension 1. So this is a line in the quotient. So this is something n minus d. Again, one would like to see this in the projective space of tangent directions.
It's n minus d minus 1.
Yes, thank you. Okay, then the projective space of tangent directions, if you remember or are familiar with the tangent spaces to the Graphman, this is E of 1 of V, and V. This is the tangent space to the Graphman at this point. And now this is embedded. There's a segregation. One to see this more easily is you think of this as P of V bar tends to and now we get to segregation. So actually there is a kind of similar picture in the very general setup that I will try to present partially. So this is only one piece of the general fact, which is not completely understood. So Well, maybe a final example, which is I will squeeze it here. We take for x the cubic surface. Okay. So it is again a very classical object of positive geometry. And as you all know, there are only 27 lines. So you cannot expect that there is a line through each point. That's not enough of them. And then the next thing you can do is to consider conics or curves of minimal degree. Now, what you will see easily is this one is covered by conics. In the following more precise sense, if you take a general point, then you find always some smooth conic for x, and all conics for x are smooth, except for special points, which are points in some plane which contains two lines. And you get these two lines. So you find that conics are a nice substitute to lines in this setting. And this is what I will try to explain next, that in many varieties, there are similar families like this conics. This will be more okay. There will be more definitions. It will be a bit more, much more advanced or fancy than what I explained here. So let me explain some basic facts on rational curves. On algebraic varieties, and the standard reference is by Pollard. Which title begins with this. There are lots of interesting results in the book. I start with constructor, which explain in more detail there. So you fix again a smooth projective, right? Complex numbers, and you want to construct a moduli space for rational curves. And the starting point is take morphisms from P1 to X. Okay. This has a structure of spin. It is this one thing of quasi-projective. Again, could be normally used. There are countably many of them, and it has an action of PGL2 by just acting on P1 by reparametrizing. And you think of this as some approximation of parameterized rational curves. And inside this, you have open subsets, which are the morphisms which are birational to their image. This here means that, again, these morphisms give you a birational map from P1 to some possible singular curves. And now this is okay, and PGL2 it's stable. And now the good one good point is that the action of PGL2 on this set is 3. Okay, and now one takes the quotient by this free action, and one gets some space of rational curves. This is a moduli space. I'm interested in. I'm cheating because there is an additional step that I will skip. One has to take a normalization. This is perhaps too singular, so one normalizes. But I'll again skip this. Okay. Maybe I should erase something. Okay. Well, it's not very time.
Here there goes for the eraser.
Oh, yes, but in Germany, use the big machine. Like a few wrinkles at home. Doesn't look too profitable. So. So we have a modular space. It's constructed in a kind of indirect way. And on a modular space, you should get some kind of universal family of curves. That will be the next step. It's constructed from here in a very nice way, direct way. So on this home space, you have a kind of universal family, which is a bit stupid, which is this map. That's a product map. And of course, it's convex with this. And you have a natural map, which is just evaluation. You have a parameter on the map, you just get a point. And all these maps are equivariant for the action of PGL2. This one is equivalent, this one is invariant. So after taking this gear and code, you get something like this. And, here we get this space of curves. Well, this map is a P1 bundle. Because it's obtained from the trivial P1 bundle by the free quotient. And, this map is just some kind of some other map. And you think of this as a kind of simultaneous parameterization of rational maps or rational curves. Okay, and then the definition that I will use is a family of rational curves. That's the components of this space. Since this space is by convention normal, I can use a connected or irreducible component. This is the same. And so what I get is like convention normal. Variety, which is traditionally denoted by some kind of K. Standard notation comes with a universal family, which is a pullback of this bundle, and there's a map X just by restricting this diagram. Well, what I will also need is a curve for X, which is Kx. Will be varieties. Okay, so now the final definition is this family is will be said to be covering. Means that for a general point, there is a curve in the family. So that means that this case is an anonymity for general X. And it's called minimum if in addition this kx is projective. Let me explain what this means.
Excuse me.
Yes.
So when you say moduli space, you don't have to consider stability, semi-stability here.
No, because this is done by this open subset beer. This is a substitute for stability, and this construction is completely intrinsic. In stability constructions, you need ample line bounding, but all these objects are intrinsically defined, and that's actually the main point of the talk. That to any variety with enough rational curves, you associate in a canonical way some invariants or some invariant spaces, and this is one of them. Okay. Further questions? Well, it's a long list of definitions, and the final one is a bit mysterious because why projective? And the idea is you have only irreducible curves in such families because these are images of P1. And you know very well, if you have a family of curves, then at the limit, the curves tend to break, to decompose into some chains. And projective says this doesn't happen. So the limit curves are still this happens, for example, for lines, because lines are parameterized by some closed subsets of the Grassmannian. This also happened for these conics in this cubic surface. They don't break at the general point, and we will see some examples of this.
This U is a subset of some X cross Grassmannian.
Not in general. Okay, so when you have this general construction, you have these two maps, and we can consider the product map. And this map is only finite. So this means that on each curve you get a normalization map which may identify points. So curves are not embedded in general. Only general curves are embedded. And right now there is no Grassmannian. There are just some abstract moduli spaces which generalize in Grassmannian systems. Okay. So let me put it in motivate lines, but I see many more. So Well, once you have a minimal family, you can get a map on this curves of this family for X to the projective space of the tangent space of X at X, which is the same as for lines. You map every curve to its tangent space. But you see, this map is not globally defined because you might have some singular curve to X. So this is just a rational map. Is not given by full X. Well, a rational map still have a well-defined closed image. Which is some varieties X. And, this one is called the variety of minimal rational planets. And there's a standard abbreviation which is Okay, the point of this whole construction is you start from a variety X and you associate some local invariant, which is an embedded projective subvariety. The original variety has no projective embedding, but this one has. And this local invariant reflects some of the geometry of X in a kind of inductive way. Because in the examples, you start with this projective space, and you found some projective space of dimension 1 less. You started with a quadratic, and you find a smaller quadratic of dimension 2 less. Or that many, you find some kind of homogeneous variety, smaller dimension. And that's why this construction is useful. And it was introduced by Mott. The main use of this PMRT is to prove rigidity of composites. Well, rigidity in a very strong sense. So this means, for example, the projective space is rigid in the sense that every family of varieties, smooth projective family, with one fiber of the projective space on connected basis, then the whole picture, family, some curve. Suppose one fiber is N. Then all fibers are also P. And the way these people prove this is you look at points here, and you look at this VMRT, which is a smaller Pn minus 1. And you look at another point. This is in the special fiber, something 0. So you put look at another point here, and here you get some VMRT. And they show that the family of VMRTs also deforms nicely. And since you started with a projective space of smaller dimension, then this one is known. And from this, you can reconstitute the global geometry of your projective space. So I'm cheating horribly because each step is really lots of work, but that's a very nice idea that I should mention. Okay. Their main application was to homogeneous varieties, which will be our next example.
If the map is only rational, why does it have?
Actually, one can show the map is birational to its image. And after normalization of the source, it becomes a morphism.
Okay.
So But these are theorems, not really the theorems. So again, the main example will be positive homogeneous variety. So by this, I mean X is the form G of P, or G is a semi-simple group. And P is a parabolic subgroup. I will also assume that this just means in terms of subgroups that P is a maximal parabolic. An example of this is Tasmanian. There are many more. And then let me maybe state a proposition. There is a unique family of minimal rational curves. And these are just the lines in the smallest embedding of X. Okay, so that's simple techniques that I should maybe. Oh. Well, first of all, what I mean by the smallest projective embedding, since the Picard group is Z, there is a unique ample generator, and for this variety it's very ample, so it's embeds X into some projective space. And, this is the one I will use. For the last one is you get just the quicker embedding, and the proof is quite easy. When I use the action of P on this space of parking curves, that by translation on the variety, and since G is connected, it will stabilize every component. So my minimal family is given by G. Okay, and then I have my base point X is the point image of P. So the stabilizer of this point, which is P, acts on this curve. Sorry, maybe not so much. This. So again, this subgroup P acts on the curve point X. Now we just use Borel's fixed point theorem. In P, we have a Borel subgroup. By definition of parabolic subgroups, and this Kx is by assumption a projective variety, so you get a fixed point. So this is just a B-stable curve in big X from this point, but now there is a limit point, which is a curved line. By two-mode decomposition, you get this, and this is actually a line in this minimal embedding. And for Grafman, it's just a construction I produced at the beginning. So well, to get everything from this simple population. So if you're very awake, you see that I'm cheating because I told you that curves are not embedded, and I'm doing as if this one was embedded. And it is because there are some further tools that I'm hiding. Notion of free curves, in which space of rational curves is smooth and behaves as expected. And since I'm in homogeneous, all curves are free. So I'm just skipping this details, but I don't want to lie completely. Anyway, so the idea of proof is okay. The details can find the machinery in Pollard's book. So actually, one can say much more on this family. This is used in this work of one mentioning. Well, I continue this example. And the theorem which says that this K consists of 1 and 2 orbits of P. And this means the smooth projective varieties is only these orbits. And actually, there's a kind of simple criterion to say if Kx is one orbit, then it will be the orbit of the Schubert line. If P is associated the long simple group. This, so maximum parabolic subgroups are classified by some nodes in the Gillikin diagram of G. Just obtained by erasing some node, and these nodes correspond to simple roots. When in a root system, irreducible root systems, there is a notion of length of roots, and there are two kinds of roots, and long and short. Except if they all have the same things, that they are all long. So, for example, this happens in for G equals SL, suppose L. Then the root system is of type A n minus 1. Then all roots have the same length, and so they are much. Because the theorem applies to Grassmann. Okay, so that's kind of nice description for projective homogeneous varieties. So this result is due to many people species. Many ones in best. Now, I've mentioned again, it's a key step to. One of the key steps to show that V of P is rigid except in one case. So that's what I want to say for. So the next case I will discuss is toric varieties. You will see it's really different. It's, the combinatorics is also quite different, maybe more familiar for most of you. Okay, so this is really challenging. So here X will be a smooth point. And then the results say that minimal families, there might be many of them. They correspond to so-called special primitive collections. And define them. So you have the usual combinatorial object on the X, it's fine, lattice of one parameter subgroups. And primitive collections are tuples of points here, where this ni are in the lattice of one parameter subgroups. They generate some rays of the fan. They are primitive generators of the rays of the fan, and the condition is that this collection of vectors doesn't generate a cone, the fan. So this this is not in the fan, but if you suppress any one of them, you get cones in the fan. So you just forget one of them, any of them. But it's not. So this is a notion of primitive collections, which was introduced by Batirev to study toric varieties. And then special means that the sum of the NIS is here. Well, that's the main result of the paper. And actually, this is a combinatorial version, but there is a very simple geometric version, which can be explained as follows. So in this situation, you can find in X toric open subset, which is a projective bundle over another toric varieties. So this will be a P, actually this is K minus 1 bundle. This is another toric variety. Of course, a small dimension. And the curves you're interested in are just the lines in the fibers. Okay. Okay. You take line in these projective spaces, and they cannot degenerate because And you will also see what happens to their tangent directions, because their tangent directions fill in a linear subspace of the projective tangent space, consisting of the tangent direction to this pk minus 1. So the complement of this is that this map from kx to p of kxx is globally defined, and its image is a linear space.
What is H?
Sorry?
What is H function?
Any number.
So we don't know what.
It can be intrinsically defined, because if you look at, I think it's minus kx t, or this is a canonical balance. This is any curve in your class, in your family, it has independency. What you find is you see, you might have many minimal families, but you have at least one. Okay, and this is not a trivial combinatorial fact, because it tells you in any smooth projective fan you get some special primitive connection, which is not so easy, at least for me. Okay, so that's the output of the paper, which is very nice. Maybe a small thing. This paper has an archived version with only 2 authors, 2 and 1, and the published version with costs 31 euros with an additional author. So I guess this one helped to correct the paper. Okay. I didn't pay the 31 euros. Okay, so that was this 2 very nice examples. And now I should give some new statements, which is where our work with Michel Brion and Nicolas Perrin comes in. So we consider complete symmetric varieties. So these are smooth projective varieties with an action of say semi-simple group. Maybe I'll take it adjoint for simplicity. This means the center is triggered. And the main condition on them is you have an open orbit. The form G mod H will be a stabilizer of some point, while H is a so-called symmetric cycle. This means that H is a fixed point of involution. Automorphism of order 2 of your group. And now we have some starting point to describe this minimal families, because we know what this tangent space is in terms of optimization theory. We describe on this board.
Can you give an example of such an A?
Well, sure. No,
G inside G plus G.
yes, not completely right. The most nicest example is you take as group H times H. And the evolution exchanges both factors. Then you see the fixed points on the diagonal. And if you look at the homogeneous space, you just get your original group H, but with action by left and right multiplication. Okay, and that's one of the nicest examples. Otherwise, you have, for example, quadrics. I think these are PGLN, modulo projective orthogonal. These are smooth quadrics in P n minus 1. You get symplectic forms, projective symplectic forms by taking the symplectic group here. So these are the kind of classical examples. Okay, so let me explain how to describe the tangent space to the variety X at some point X, which is with the base point, the point with as the group H. So this is supposed to be tangent space to the open orbit. And this is the portion of Lie algebras. Now you have a decomposition of the Lie algebra of G. Because it has an action of this evolution sigma, and Lie of H is a fixed point subset. The complement is noted by some Gothic in some approximation to it later. So this is minus sigma. So what you find is this Gothic P. Now this has an action of H. This is a representation of H, which is very well understood. It's the kind of primary representation of this symmetric space. And the G mod H is so-called irreducible. In the sense that you cannot decompose it into a product of simple symmetric spaces. What you get is that either P is irreducible, or P is the sum of two irreducible representations. Okay. Another remark is my highest weight theory applied to this group H, which is reductive. In an irreducible representation, you have a kind of natural line, which is consists of the highest weight vectors. So you get the highest weight line. And here we get two of them. And, one can show that these two lines are tangent lines to some very special curve, rational curves. So we got some special rational curves which kind of exponentiate its tangent lines. And one thing I can state some versions of many results without too much clicking. Now is what we proved that for G model indecomposable, irreducible, sorry. Then this X has one or two linear families. And this is just an abbreviation for a family of minimal rational curves. And these are very close to the orbits of these lines, of these special curves. So this KS contains these orbits, so I can add my distribution of C. This is for sure, but in general, you have equality. And either or as divisors. So these orbits, again, they give you either the whole stuff or some divisor. And in the second case, this Kx is homogeneous under G. Okay, so that's maybe some improved. Well, we can show this, but we don't really understand why, because you see on this object K, you have a G action. On Kx, you have a natural H action, but you don't have any G action on H. And the same holds for this representation. P, you have an H action, but you definitely have no G action. So this G action here is something we can construct by using the classification of symmetric spaces. So this comes out of the way. But the result is that this families are homogeneous. And in addition, what we get is that the tangent map is closed in motion. This is a map which associates each curve is the direction of tangents. So finally, finally that's not okay. Maybe I give a short example where this phenomenon occurs, and then I explain. Because otherwise, maybe I just grab another board.
Put the front one further down, Alexis.
So let me take H times H mod times H. This example one. H is EGL. And then there is a natural compactification of PGLN through matrices. This is not the one we use. We use some compactification which are have a nicer orbit structure. Compactification, you see the orbits are just strata of matrices or lattice, right? And there is a construction in classical geometry which consists in blowing up the strata from the smaller one and going to the top. So this is the sequence of blowups. And here it's a projective space, so you have the lines which form a very nice minimal family. And here you have a strict transformist. Of some lines. I want to detail. Not all lines survive to be minimal here. Only those which have a very special behavior. And what you find for these lines is here is well, I should explain what this P is in this case. P is just a real algebra of H. So this is the EG and N. This is homomorphism of Cn, and then multiples of the identity, just by definition. And in Mn, you get this is for Cn. That's Cn. When you go to the projectilization of this, what you get is the same object that we had before, P of Cn star times P of Cn. This goes to P of Mn, and this goes to this. The composition is injective, and this is this Kx. So it's a product of two projective spaces, and the closed the divisor. This theorem is just the incident variety. Here you have a hyperplane and a point. We can have the incident variety. This is just a divisor, homogeneous divisor. And on this space, you have an action of H times H by both factors, but you should have only an action of H, and that's how it goes. So, but you see, it's just a very explicit construction, and at the end, you find it's actually, I don't know any example of a non-homogeneous Kx in the setting of varieties with an open orbit. If you have positive toric varieties, this Kx is homogeneous with the positive space. But again, there is no natural group action. So I should definitely